So welcome everyone to the third Aussie session of RQI-Online 2020-2021. Exciting title for this conference, I love it. And for our first speaker, we've got 4 speakers in this session, and the first one is Lucas Hackle from the University of Melbourne, and we'll be talking about adiabatic vacua from linear complex structures. And as always, if you have questions, you can type them or speak them at the end. I'm fine with either. But please, and if the speaker wants, we can do questions during the talk, but I will leave that up to Lucas. So I'll turn it over to you now, Lucas.
Yeah, I think I'm totally happy. So I just opened the chat on a second screen, and I hope to see questions. Otherwise, I'm also happy to discuss at the end. And it seems like that we are a small enough group at the moment, so that if you have anything, just write or maybe even interrupt if you prefer. So yeah. Okay. So I should just start.
Yep, you can start.
Okay, great. Yeah, it's a great pleasure to speak here, and thank you very much for putting together this very nice global online RQI conference. My talk will be about adiabatic vacua from linear complex structures. So let's start with a quick motivation. So we are all familiar with the scalar field in, for instance, a cosmological FLRW spacetime. And such a scalar field can represent matter fields or linear perturbations of a gravitational field. But in contrast to a flat spacetime, there is typically no unique vacuum state that we can choose that has like 0 particles and is invariant under the symmetries of the spacetime. Why? Because in many situations, the spacetime itself does not have the maximal number of symmetries. I mean, for certain spacetimes, one can define something similar, like a vacuum state as in Minkowski. But in general, curved dynamical background spacetimes, this will be difficult. And so the question is, what state do we put our quantum field in to then study, for instance, particle production? And Parker introduced in '69 this notion of adiabatic vacuum, in particular to study particle production in FLRW, and has since then been used in various contexts, in particular in cosmological studies of preparing initial states in cosmological spacetimes, but also in general to study particle production in dynamical background geometries. And what I'm aiming for in this talk is to introduce to you a new method to define the same notion of adiabatic vacua based on Kähler structures, or in particular complex structure, and to hopefully convince you that it's very interesting to use these methods that will be more powerful for certain contexts. But wherever WKB, the standard approach as introduced by Parker, works, the two will be equivalent. So in terms of structure, I will begin by a brief review of the mathematical tools to study Gaussian states, and then explain a connection between adiabatic vacua and so-called Lewis-Riesenfeld invariants that also appear in other areas of physics. And then finally come to the main result, namely defining adiabatic vacua through an asymptotic expansion of the so-called linear complex structure, being equivalent to WKB, but different in terms of the method. Now, let me start with a review. So this is largely based on this recent paper with Eugenio Bianchi, where we tried to explain a unified framework to study both, or describe both, bosonic and fermionic Gaussian states. And maybe just to emphasize why are these vacua also called Gaussian states? Probably most of you will be familiar with it. They satisfy Wick's theorem we consider typically in curved spacetime quadratic Hamiltonians, so non-interacting fields, just because non-Gaussian states and non-quadratic Hamiltonians plus a curved spacetime is extremely hard to treat. I mean, there are some approaches by Robert Wold and others, but more or less most of the methods to study quantum fields are based on free fields, so quadratic Hamiltonians and therefore Gaussian states. And using these methods will also allow an easy generalization to fermionic Gaussian states, so also fermionic fields. Now, what are these methods based on? Well, first, we look at the classical phase space of n degrees of freedom, which, of course, when we go to a quantum field, we will take n to infinity at the end. So we have a system with n creation and annihilation operators that satisfy either canonical commutation or anti-commutation relations. And now the basis of this formalism is to move to a basis psi that has two n operators that I call Q and P, but I call them Q and P for both bosons and fermions. So they're constructed from the creation and annihilation operators in the standard way. And now I only talk about these psi, where these Q and P's are organized. And they satisfy, for bosons, the standard commutation relations, and for fermions, standard anti-commutation relations, where omega is an antisymmetric non-degenerate matrix, so it's also known as a symplectic form, while for fermions, the anti-commutation relations will ensure that G is symmetric and positive definite, so a metric or positive definite inner product. And for most of this talk, I will focus on states that do not have a displacement, so the expectation value of these psi's themselves, that later for quantum field will become the field phi and the conjugate pi, the momentum conjugate, where their expectation value vanishes. And in this case, you can look at a two-pair correlation function and always decompose it into a symmetric and an antisymmetric part. And the point here is, for bosons, this antisymmetric part is, of course, already fixed from before by the commutation relation, but for fermions, the symmetric part, G, is fixed. But in general, the two-point correlation function will have both, and the other one will not be fixed by the relations, but will depend on the state. So for bosons, G will depend on the state. It's still symmetric and positive definite and known as the covariance matrix. And for fermions, it's that omega is antisymmetric still and fully determined by the state. And it's also called covariance matrix, or fermionic covariance matrix. Now, having introduced kind of this picture with omega and G that satisfy the conditions of a symplectic form or metric, we can also introduce their inverse matrices that I denote here by small letter omega and small letter G. We can complete this kind of collection of two structures by a third structure called the linear complex structure that also is in the name of this talk and will play a major role in describing Gaussian states. Now, if omega and G are compatible, then you can use the equation that I write here in the middle to define a third structure J that squares to minus identity. And it's called linear complex structure because on the classical phase space, this J essentially represents a notion of imaginary unit that squares to minus identity. And in fact, when you have such three structures, G, omega, and J, that square to that satisfy the conditions indicated here, then you have a triangle of compatible Kähler structures. And they are always related by this equation. And exactly such a triangle always comes up and exists automatically if you have a Gaussian state. So let's explain it in order. So we take any state psi, such that the expectation value of psi vanishes as before, but just we don't know anything further about the state. We can then decompose the 2-point correlation function into a symmetric and antisymmetric part. And in general, just knowing this 2-point correlation function doesn't help you at all if you want to compute higher order correlation functions. So if you have n of these psi. However, if the state is special, namely if it's a Gaussian state, you have this very famous property of Wick's theorem, where you can compute any higher order correlation functions using Wick's theorem. So by just contracting the 2-point correlation function, either the symmetric one for fermions, for bosons, or the antisymmetric one for fermions. But these formulas that I write here, they are actually valid for both bosonic and fermionic Gaussian states. And it's exactly for these special states that G and omega are compatible, such that the J that is formed by writing this equation satisfies that it squares to minus identity. And those can then be labeled by J, because J contains all the information about G and omega that depends on the state. And they are called squeezed vacua or just Gaussian states. And that's what this talk will be about. Now, knowing J, we can conclude what the corresponding state J is with this very compact equation that intuitively is just the projection equation saying that the state J is the vacuum 0 associated to a certain set of annihilation operators that is now encoded in the matrix J. And this gives us a single equation that connects the matrix J with the Hilbert space vector J. And from that, we can study time evolution very efficiently. So if you have a quadratic Hamiltonian with a Hamiltonian flow on the classical phase space, then the covariance matrix G, the symplectic form omega, and the complex structure J just evolve by contracting the evolution matrix M from both sides to G, omega, and J. And also something that often plays a role in the context of studying Gaussian states is that you can compute the entanglement entropy analytically in terms of a certain spectrum. And you can phrase it in terms of the covariance matrix, but if you want to have it in a unified way, then the formula that I provide here is valid for both bosonic and fermionic entanglement for a subsystem that is the result of restricting this big matrix J, in our case a 2n by 2n matrix, to the subblock of a 2na by 2na submatrix. And then you can compute the entanglement entropy very efficiently using this trace formula. So in summary, in this part, we have this picture of bosonic and fermionic Gaussian states, where we have a background structure for bosons, the symplectic form, for fermions, the metric that defines commutation or anti-commutation relations. And then we have the state-dependent structures that are either covariance matrix, G or omega. But in both cases, equivalently, we can use the complex structure J to fully encode everything that there is to know about the Gaussian state J. And just to give you a glimpse of how far you can push that, you can really write a very long table that we also put out in this paper I mentioned. We can really go parallel through bosonic and fermionic systems and show, okay, you have a certain structure for bosons, then you have a different structure for fermions, and line them side by side. And you see that it's really a unified picture where the bosonic and the fermionic system share a lot of properties for computing entanglement, for the representation theory of the symplectic orthogonal group, how you get a double cover. I mean, it's very nice and unified, but is it also useful? And I want to give you in this talk one example, namely for adiabatic vacua. You can very efficiently use that. So just for now, let's focus on bosonic states, because bosonic quantum fields are the standard case that we consider in curved spacetime. So now we can even allow for displacement. This is a picture where we represent our Gaussian state as a quasi-probability distribution on the classical phase space, where G essentially describes the shape of the Gaussian, how it's squeezed, and Z describes the displacement if we have one. In most cases, for quantum fields, we will choose Z to 0, so the Gaussian is centered where field and momentum, so Q and P or phi and pi, will vanish. And then we have this decomposition I described before of the 2-point function into G and omega. And if we now go to a quantum field, so infinite number of degrees of freedom, but in a homogeneous and isotropic spacetime, we can do a Fourier transform, and we can look at fields phi and pi for fixed momenta, and we get a delta distribution, so there will only be correlations between them where the two Ks are the same. And so we can really, I mean, that's the whole point of doing a Fourier transform, that we decompose in individual blocks of momenta. And in these blocks, we only deal with 2x2 matrices. So the symplectic form is just a 2x2 matrix. The 2-point correlation function in this block is just a 2x2 matrix. And in particular, the covariance matrix, G, only depends on the momentum. And we get a 2x2 matrix with entries P of k, pi of k, and x of k. So essentially, we have a tensor product of lots of one-mode Gaussian states for each momentum k. Now, we can compute the linear complex structure J using the formula that I explained before. And it's really just a rearrangement of P, X, and pi. So this is the matrix J. And it's important to remember that this is also still for each momentum K. Now we have conditions. We know that G needs to be larger than 0 if this describes a proper physical state. And we also know that J squares to minus identity if it's a Gaussian state. And that can be translated into certain conditions for these functions P, X, and pi. And in particular, we can then solve for pi. So we only have two free functions, P and X. And we can still label our Gaussian state in this way, as described before. And if we now have a Hamiltonian, a quadratic Hamiltonian in our spacetime, we will look at something like this if it's homogeneous and isotropic. Namely, the Hamiltonian will also decompose into different momenta. And we look at different time slices where we have some arbitrary functions V of P, V of T, that depending on what cosmological spacetime you're looking at will be different. But in the end, you get a bilinear matrix that describes what time-dependent Hamiltonian you have. And this time dependence, of course, comes from the dynamics in the background. You can use this matrix H to contract it with the symplectic form omega to get a symplectic generator, which is a 2x2 matrix for every momentum K of this form. And then the time evolution of the state, which we can phrase in terms of J, is fully encoded in solving the time evolution equation of psi classically with respect to a time-dependent Hamiltonian, so a time-dependent symplectic generator K of T. And the solution can be written through the symplectic transformation M of T that is a time-ordered exponential. And so if we have solved this and we know the initial state as J of 0, we know the time evolved state at different times just by contracting again with the matrix M of T. So this 2x2 matrix K is put in this time ordered exponential. And so we will get for every momentum 2x2 symplectic matrix M of T. And so, of course, also the covariance matrix will evolve in this way. So all this is very standard, but just written in a way that we can talk about the next steps. So let me now explain to you how adiabatic vacua are connected to Lewis-Riesenfeld invariance. And for that, of course, let me also review briefly how adiabatic vacua were introduced into the literature on quantum field theory in the curved spacetime at the first place. So the standard example to introduce an adiabatic vacuum is just a harmonic oscillator with a time-dependent frequency. So that's also, if you read Beryl Davis, for example, the standard way to introduce it. But of course, what this Hamiltonian here represents is the Hamiltonian of a single momentum mode. So if we put it in a quantum field, we would have such a time-dependent Hamiltonian for each individual mode of our quantum field. Now, a first intuition of what an adiabatic state could be, like a state without particle, would be to define the ground state of the Hamiltonian at a time t0. This would be a perfectly fine state that would not evolve at the time t, but the problem is our Hamiltonian changes over time. So if it's the ground state at a time t0, it will not be a ground state at a later time, and in fact, generically, will change rapidly thereafter. So it might be a good vacuum at one time, but it will not be a vacuum for a period of time. And that's exactly where WKB comes in, where one says, well, we would like to have a state that changes slowly under time evolution, and that adiabatically describes a notion of state with zero or very few particles in it, with respect to a notion of particle that also changes as we move through different time slices of our space-time. And the way this is approached in the standard way is to convert this Hamiltonian in a second order classical differential equation for the coordinate q of t, and then solve it using WKB. So we extract out of this differential equation an equation for this function of time w that is complicated and nonlinear. However, we can solve this equation for w order by order if we introduce a smallness parameter, or also adiabatic parameter t. So we rescale our time coordinate by t and do then an order by order expansion for large t in w. So we still have the solution q of t, but now we solve the differential equation order by order in w. And so the zeroth order, w of 0, w0 of t, will just be omega of t. So that's where we ignore all the higher order terms. But then we plug this zeroth order back in. We see that there's no first order, but there is a second order where we then get derivatives of this omega. And so there we see that the explicit time dependence of our frequency omega now plays an important role. And this can be done order by order. And once you have solved that, you can define your adiabatic vacuum in terms of the Bogoliubov transformation that results out of this classical solution that is done order by order. And in many situations, it's enough to find an adiabatic vacuum at a given time, t0, where you do this expansion, up to a certain order, up to fourth order, for instance, to renormalize your stress energy tensor, and or whatever order you want, if you can compute it. I mean, if this truncation works well. And in systems where this omega of t, this time-dependent frequency, is an analytical function in time, this is no problem at all, and often you can even go to infinite order. But for most practical purposes, when you do computations, it suffices to do it up to a certain order. Now, let me tell you about the connection to the so-called Lewis-Riesenfeld invariant. Well, this is something introduced not at all in the context of quantum field theory, but really just for quantum mechanical systems where you have a time-dependent Hamiltonian h of t, then another operator, I of t, a time-dependent operator, is called Lewis-Riesenfeld invariant if its total time derivative vanishes. So if we have the sum of the partial time derivative plus the commutator with our Hamiltonian. And if you have such an invariant, you know that the expectation value is preserved under time evolution, and there are lots of results known also how the time-dependent eigenvectors of I of t are related to the ones of h of t, and so on. Now, we have such a special operator associated to every Gaussian state J, namely the associated number operator, that can be written in this compact way if you compute the corresponding G inverse and omega inverse, not a little g and little omega, associated to the Gaussian state with complex structure J. You then have this associated number operator that is just a sum of the individual number operators. And it's the unique vacuum. I mean, this number operator is defined in such a way that the state J is the unique vacuum associated to this notion of number operators. And that now draws the connection between Lewis-Riesenfeld invariant and time-dependent Hamiltonian. Namely, if you have a time-dependent Hamiltonian and compute the adiabatic vacuum J of t at infinite order, so in that case you have such a adiabatic vacuum for every time t and it's unique, then the associated number operator n of jt at a given time t defines now a trajectory of operators, I mean of I of t, and this collection, this time-dependent set of operators is exactly the associated Lewis-Riesenfeld invariant. And that's how, whenever you talk about adiabatic vacua in quantum field theory, you can equivalently also talk about the associated adiabatic number operator, which is this Lewis-Riesenfeld invariant satisfying the equation up here. Okay, so this drew this connection. Now let me tell you about the adiabatic vacua, how you can compute them from J. And this slide essentially contains everything you need to know. We do similar to WKB and asymptotic expansion. So you still do something order by order, but you don't do it with a classical equation of motion, but you do it directly with a linear complex structure J. So you write J of t as a power series with some parameter lambda, and you write your differential equation where we have our G of t that we want to solve the time evolution from, and our symplectic generator for bosons, K of t, but it could also be an orthogonal generator if we want to do the same thing for fermions, where K of t, I mean, I introduced it to you before, it's here this K of t that is extracted from the Hamiltonian for a given momentum, if we want to do it as mode by mode. And having done this, we get this linear differential equation for J dot, which we can now solve order by order using this parameter lambda if we introduce this asymptotic expansion. And if we now want to extract the adiabatic vacuum up to order m, we just take this asymptotic series that we solved iteratively up to order m and set lambda equal to 1. Now, why is this relatively easy to do? Well, because it's just a set of algebraic equations at the time t where we do this expansion. So, for example, at 0th order, we find that J0 is just a state that commutes with K, J that commutes with K of t. So it's just the instantaneous vacuum. Just in the same way as for WKB, the 0th order term was just the standard instantaneous vacuum of the Hamiltonian. But then we can go to the next order, and the next order, and so on. And what we should not forget is that we also need to require that J describes a proper pure Gaussian state, meaning that it squares to minus identity. So we should also have a condition on J0 and coupling between J0 and J1 and so on. And so overall, we get here this condition 1 and this condition 2 that we can do, which is sufficient for us to compute J0, J1, J2, and so on, order by order. And these equations, if you look at them, they are always linear in the new order that comes on top, except here for J0. For J0, the 0th order is that it squares to minus identity. So that you need to solve once, but once you have done that, the next term allows you to solve for J1 in terms of J0 and derivatives and so on. But in the end, you will have collections of algebraic equations. So that's the method that really just follows from doing the same kind of applying the same idea as for the WKB, but now all written in terms of J. So let's just give an example for this time-dependent harmonic oscillator with this time-dependent frequency omega of t. We construct this 2x2 matrix H that defines the Hamiltonian, construct the symplectic generator that only has this dependence of omega of t, and then compute the 0th order, which is the time-dependent Hamiltonian, the time-dependent instantaneous vacuum at time t0, and then do the recursion relation for the next order. So for instance, J1, J2, and so on. And if you then translate this to the resulting states that you would get from the WKB, you will find perfect agreement with what, for instance, is presented in Birrell and Davis. So that's so far is very good. We have the same results. You can now use that to, for instance, plug in the results for FLW spacetime with different scale factors. So you have
Lucas,
the Zitter space.
Can I interrupt for
yes.
just 1 second?
Sure.
So you've got 7 minutes left in the session, including questions.
Okay, that's very good. Yeah, I'm almost done. Yeah.
All good.
Perfect. So we have the Zitter spacetime, radiation-dominated spacetime, and matter-dominated spacetime. And what you see here are the resulting solutions up to 3rd order in J. So you then can translate it in terms of the function P and X. Okay, so let me wrap up exactly at this point to give a summary and outlook. So in the first part, I explained to you why covariance matrices and complex structures are very useful to describe Gaussian states. And in the second part just now, I explained to you how you can get adiabatic vacua in terms of an asymptotic expansion directly of the complex structure. It perfectly agrees with WKB as introduced by Parker. And you also get a natural expansion in powers of K. And as an outlook, you can use that to then investigate the stress energy tensor, and more importantly, explore adiabatic systems that cannot be easily treated with WKB. For instance, if you do not have individual decoupled modes due to the Fourier transform, but coupled degrees of freedoms or fermions, then doing WKB is much harder, or partially even just not known or not done, because the equations will get very horrendous and coupled, while in principle, above asymptotic equations that lead to these algebraic equations are still just linear algebra that you can solve. And the third part is you can use the same techniques also to define adiabatic mixed state at a fixed temperature, in which case you would lift the condition that J squares to minus identity. In this case, you do not require this pureness condition. So those are examples that we will be studying in the future. So many degrees of freedom, fermions, and mixed adiabatic states. So that was my summary, and thank you very much for your attention.
Okay. We can do little clap icons. Let's see here. There it is. All right, that's a very nice connection. So Edu has a question. So Edu, why don't you kick it off?
Yeah, yeah. Sorry, I can't use the raise hand because I'm host. I don't have that option. That's very badly designed. Thank you very much.
Option? Really?
Oh, yeah.
That's
no,
weird. Okay.
Yeah, I know. Lucas, thank you very much. It was a great talk. Enjoyed thoroughly. I have a couple of quick questions. One of them is the adiabatic vacuum built this way. Well, in the cases that is exactly equivalent to the usual WKB way. I know the answer, but in general, is this guaranteed by construction to be a Hadamard state?
So that's a good point. So I mean, here adiabaticity is really just defined in terms of the quantum system. No? So at this stage, if you put in some weird Hamiltonian that has some weird coupling between different momenta and whatnot, you would still at least formally define an adiabatic vacuum. And of course, if you have a crazy Hamiltonian, it will not be a Hadamard state.
Right.
Now, you could ask, okay, what are exactly the conditions on a Hamiltonian such that the corresponding adiabatic state is a Hadamard state? And I think that this has been studied to some extent, but I don't know the exact answer of conditions.
I think Verge, right? Verge works, right? Verge studied this kind of thing a little bit.
Yeah,
I don't quite remember from the top of my mind. I was wondering if this construction already guarantees somehow. I don't see it right now, and I said wanted to know.
Yes, no, it doesn't guarantee it, but essentially the conditions are exactly the same as for for WKB, and they go back onto the Hamiltonian. If you have some crazy Hamiltonian, like, I mean, of course, most people, because WKB almost exclusively works for states where you have this Fourier transform and decompose into different momenta, then you can just say easily, under these conditions, if the Hamiltonian satisfies these conditions, it will be a Hadamard state.
Right.
Because this method now here would in principle be more general and would allow for more interesting Hamiltonians. I don't know for what Hamiltonians the corresponding adiabatic state will be Hadamard. But it's not a question of the technique. It's really just a question when is the adiabatic state associated to a Hamiltonian Hadamard.
Right. Then the second question I had is for this systems of coupled degrees of freedom, right? Like, I mean, you cannot really do it for any coupling. Yeah? You need to be quadratic or something like that because you want to be, you're considering quasi.
Yeah. So, okay. So this was maybe not very well said. What I meant with coupling here is not coupling of, I mean, that you have really interaction in the Hamiltonian, but that your Hamiltonian has entries that couple different momentum modes, so that the Hamiltonian is not diagonal, so cannot be diagonalized by Fourier transform. So, for instance, that you have k and minus k, certain interactions. That would be the simplest case. Or if you look at finitely many degrees of freedom, then of course you could also treat it with finite dimensional matrices or approximate it and have some crazy interaction between different modes, or even don't use Fourier transform.
Yeah, I thought as modes couple as you would couple harmonic oscillators, right? I mean, kind of a quadratic coupling.
Exactly. Yeah, and in that sense, this method will allow you to do that. Okay. So we did it, for instance. I mean, most of it are, of course, simple toy models where you can do it. So one system was just two harmonic oscillators, which if you treat it in WKB is pretty damn hard. And here it just comes out naturally. Or another example is, for instance, if the Hamiltonian has more complicated forms where the standard kind of cosmology perspective uses these Mukhanov variables in order to bring it in a form where you can apply WKB. Here it just comes out naturally if you do this expansion. Yeah. You don't need to change variables.
Yeah. All right, wonderful. Thank you, Lucas. Very interesting.
Thanks.
Yeah, thanks, Lucas. I'm just wondering, is there, super quick, is there an analog of this for finite dimensional quantum mechanics? Because I do a lot with Gaussian states and quantum computing.
Yes, I mean, in fact, everything that I presented here is absolutely valid for finite dimensional systems as well. I know that people have studied also adiabatic states for finite systems. I don't think it has been studied so much, and to our knowledge, we were the first to write it in this way using linear complex structures for the purpose, or I mean, with this expansion that I presented.
Right.
But everything that I wrote here works perfectly well also for finitely many degrees of freedoms, both bosons and fermions.
Right. Okay. Well, thanks very much. Let's everyone thank Lucas again. Oops, not raise hand, lower hand. Clap. There we go. All right. Thanks, Lucas. So the next speaker is Carolyn Wood. And I'll give Carolyn a moment to get set up. Hello, Carolyn.
Hello, how are you?
Very good. Can you just steal the screen, or does Lucas?
Have to wait a bit. Yep, now I'm good.
Are you able to share?
Yep. Oh, sorry. Okay, how's that look?
That's the slides. Do you want to do? There it is. Okay, all good.
All good.
Yep.
Cool.
So take it away, Carolyn. Should be is it UQ talking about Gaussian states don't propagate semi-classically in spacetime. All right.
Thank
Good
you.
to know.
Well, good morning or good evening, wherever everyone's joining me from. I'm a PhD student at the University of Queensland, working with Dr. Magdalena Zich. Despite my slightly provocative title there, some of you may be familiar with this general concept from a previous talk I've given. And you can also check out this freshly published paper that came out last month, if you'd like to know more. So I'll begin with a background and some of the motivation for this talk and this work, and then I'll take you through the derivation of these new minimum uncertainty states that propagate semi-classically in spacetime, and some of the interesting properties that they have that we've come across. And then I'll finish with a little bit of touching on what future directions I might have. Okay. So I expect many of you in the audience are familiar with this idea of using composite particles, that's atoms, molecules, as clocks. So what do we mean when we call them clocks? Well, we're talking about a particle traveling along a world line with internally evolving degrees of freedom that track proper time. They're governed by a Lagrangian such as this. And generally this is idealized as a point-like particle in a static symmetric metric with a Hamiltonian of this nature. And its rest energy is of this form. So it's at this point that we're particularly interested in this concept of mass energy equivalence and the rest energy being equivalent to a mass, which takes us to this next low energy regime, where we have a classical sort of external degrees of freedom, but the internal relativistic dynamics remain. So while something may look like a contained classical object on the outside, internally it's still our little clock. However, for purposes of this talk, perhaps it's better to go back to this undergrad sort of idea of the internal energy level structure of an atom, if that helps conceptualize. So if we introduce the mass energy equivalence, these energy levels have associated masses. And this introduces the concept that we might have a quantum mass uncertainty. So in the low energy regime, a Hamiltonian for a particle like this might look like this, where we have the rest energy of the particle, a kinetic energy term, and you may also have a gravitational potential energy term. And you'll note that I've got hats on all my M's here to denote this concept of a mass uncertainty. And when I write that, I'm indicating something like this, where we have some sort of low rest mass ground state of the internal energy, and then some higher order terms. And I've kept this as a H int rather than just masses, because this may include any other internal degrees of freedom of the particle. Yeah, so if we consider such a particle as a quantum state in a superposition of mass energies, how does it behave? So a problem has actually arisen from this question, where previous studies which have taken such a particle and propagated it have found that the internal mass energy states delocalize. So if we start with some superposition here with the dotted lines, and then propagate it for some time, each of the mass states travels at a different velocity, and they eventually end up all spread out like this. So this seems a little strange, perhaps detrimental, and also a little strange if you're used to working with Gaussian wave packets, because we expect them to have the most classical or most localized trajectory, and we don't want this kind of behavior necessarily. But perhaps with this new formalism, this is what we might expect. So thinking a bit more deeply about that, certainly it's going to be a problem for experiments with composite quantum systems. And if we are thinking of quantum clocks and we want to use atoms as those clocks, then that starts to be a questionable model too, because it sort of seems like a clock traveling along and leaving its hands behind. So clearly this needed some more depth of thought. And this is where I jumped in. Let's look a little closer at the trajectories of these particles. So when we think of a trajectory in the real world, which is space-time, we use the particle's position and velocity to define that trajectory. And this is a concept we've been aware of since we first started throwing objects as toddlers, or even in high school physics class with parabolic motion. So as physicists, we also take it for granted that the Gaussian states will have this most localized trajectory, and that we can transform back and forth between a position of momentum space and a position of velocity space. But with the mass operator in the mix, we can't simply divide through by m to transform between momentum and velocity. So yeah, so it's no longer trivial to transform between phase space and configuration space. So we need to go back to the beginning and define a velocity operator from scratch without having to go via momentum. And that might look like this. So we can derive it directly from the Hamiltonian. So with this position and velocity operator concept, the next step was to find a state that minimizes position and velocity and not worry about position and momentum for a little while. Now we can create a uncertainty inequality for any two quantum observables, and we know that the resulting minimum uncertainty states will be unitarily equivalent to any squeeze states. So the mechanism here is quite familiar, perhaps. We have an eigenvalue equation to find this state that will look quite familiar. We've got the Bogoliubov transform over here and the displacement off the axis, if you want to think of this in some sort of parameter space like that. But my notation here is hiding a lot of complexity that I'm going to explain now. these creation and annihilation operators here are actually based on this idea of base spectra of masses and are each equivalent. They're a set. They're a set according to the different masses. And the state here is also subject to that, where we have a tensor product between these individual states that are each entangled with a internal mass energy. So a more telling way of writing this would be perhaps with these sums in the mix. And it's important to note that those mass sums have to be there from the beginning, and part of the equation that we need to solve to find the minimum uncertainty states. So in solving this equation, this is our resulting position velocity minimum uncertainty state. It may have some familiar elements there, but most importantly, we need to point out this mass that is at the front of all of these other terms and scaling it. And also, once again, this sum over the mass states is part of the state itself. So individual components of this are not position velocity minimum uncertainty states when we're using this mass operator formalism. So one state with a fixed mass propagating will have a known center of mass, and its momentum will be dependent on mass, and its width will also be dependent on that mass. So let's compare it back to a generic Gaussian such as this, which we usually will come up with whenever we want some sort of Heisenberg uncertainty principle minimizing state. If we put a state like this in a superposition of masses, I've used 4 for my plot here. So we've got this superposition state here, and using a propagator derived by path integral formalism, when we evolve that over some time, the component mass states spread and separate, just as I showed you earlier. So you've got the superposition state there dotted, and then I've got the individual mass states there for illustration. So in this case, momentum and variance are not dependent on the masses, but the velocities of the individual centers of mass of the peaks are dependent on mass. So that's why they all spread out, because they're all traveling at different velocities. The lightest mass ends up way in front, and the heaviest mass ends up lagging behind. So turning to my minimum uncertainty state.
Yeah, it's really good.
Sorry, is there a question? Oh, sorry. Okay.
I'd like to remind everyone to please stay muted. I'll mute you if you don't. Go ahead.
Sorry, I can't see any of the Zoom window from here because I've only got one screen.
Oh, yeah,
Okay.
yeah. No, there's no questions yet.
Yep, I assume you'll yell at me if there is. So.
I will politely let you know at the end.
Yep, thank you. Right, so taking one of my new minimum uncertainty states with the same 4 masses, it initializes looking like this, where the dotted line again is the superposition state overall, and I've got the individual masses plotted over the top for illustration. Now remember, in this case, momentum and variance are dependent on the mass. You can see already that the variance is affecting the width, the mass is affecting the variance at the initial stage, and the velocities are now not dependent on mass. So applying the propagator, same propagator as before, we find that the whole state moves cohesively together. And the overall width also spreads out as we expect in position space. So this is interesting. Even just visually, we can see that there's obviously a difference in the behavior between this generic Gaussian and this new minimum uncertainty state. But what's the actual quantifiable effect here? So if we consider a generic Gaussian with just 2 mass states, with a nice big energy gap to really show up this effect. The peak separation will be dependent on this energy gap, as well as the mass of the ground state and the velocity that the whole thing is traveling at. And to plug in some numbers, we'll take strontium atoms as the standard, because these are the state of the art for quantum clocks at the moment, or at least these two sources that I've taken the numbers from were cutting edge at the time. And taking the numbers from those experiments, we have a peak separation of 10 to the minus 9 meters per second. So if we compare that to strontium's de Broglie wavelength, we find that the delocalization grows beyond the de Broglie wavelength of the atom within a millisecond. And that is the order of magnitude of the timescales that these experiments are currently operating on. So it is a significant effect, and it's only going to become more significant as we become more precise with such experiments. But we don't just stop there with the actual delocalization of the states. Sorry. If we just look at the variances alone, this is a term for the variance of the Gaussian, and this is the variance of my state. If we set these initial variances to be equal, we find that the minimum uncertainty state is more narrow than the Gaussian at any particular time step that we are looking at. So there's something interesting going on there with the states themselves, not just the way they're moving in phase or configuration space. So all this analysis so far has been done with just position space, but given that these are working in two parameters each, I'd like to compare them each in their native spaces. So for this, I have turned to Figment distributions, and now you can really start to see how they're behaving differently. So if we think of this as states in a superposition of three mass energies, and they began at the origin here and have evolved as free particle Wigner functions, hence the sort of squashed and turned aspect to them. So the generic Gaussian state that I showed you at the outset, imagine looking at it from the side here, the mass components have all moved apart from each other, but they have a common momentum. Whereas my equivalent minimum uncertainty state has the common position, but they are able to take on different momenta. If we then move both states into configuration space, you'll see that the generic Gaussian delocalizes in both parameters there. However, my However, my minimum uncertainty state stays completely localized. So this is indeed the minimum uncertainty state in this parameter space. So that's pretty cool. Some more interesting properties that we've come across through analyzing these further. There's this idea of contractive states, which some of you may be familiar with. And these are states which, upon propagation, initially undergo a narrowing in their variance before then continuing to evolve normally. And a generic Gaussian in this form, as you'll see on the right here, each of the mass components undergoes this narrowing at a different time. And my minimum uncertainty state, all of the states undergo this narrowing at the same time. So if you were wanting to use a state like this to beat the standard quantum limit, which is one of the applications they've been looked at in the context of, you might want to look towards a state like mine, because it will stay cohesive for all time. And also looking at boosts. When you boost one of these generic Gaussians in a superposition of masses, because they have different peak momenta, you won't have two observers in different reference frames agreeing upon what the behavior that they see. So they won't make suitable clocks in those contexts. However, my minimum uncertainty state transforms covariantly via a boost generator that includes the mass operator that I've defined before, which means that observers will agree through appropriate transformations on the what they're seeing. So if you are looking for idealized relativistic quantum clocks, once again, these might be the states that you should be considering using. Which brings me finally to a double slit scenario. Now, some of the previous studies that looked at these superpositions did use a double slit scenario to fully show the strange behavior, and a particle in free fall in one of these generic Gaussian states was found to, as it separates, each of the components are traveling at different speeds, so they're arriving at the screen at different times. So they are interfering at different places on the screen, which of course totally washes out the interference pattern, and was put forward as potentially the true physical reason for gravitational decoherence. However, a particle in free fall in one of these minimum uncertainty states will not delocalize like that. The whole state travels together. It still will drop in the gravitational field, but it will hit the screen all at the same time. So that's good, but nonetheless, the interference pattern was still suppressed, which perhaps suggests that there are a couple of different mechanisms at play here, a decoherence related to time dilation, and then a decoherence related to this delocalization effect, which will be dependent on the state that we choose. On the right here, this is interference between a spatially separated state that is equivalent to a double slit scenario, with this propagation that delocalizes taken out of the mix. So it's just being allowed to evolve in place. And you can see here there is a difference in the interference patterns of the two different states, the black line being the superposition and the colored lines being the different mass components. You can see that the XB minimum uncertainty states interference pattern stays more pronounced for a given time slice. And as we go to higher orders of masses, you can see that effect a little even more prominently. And in the far mass limit, even then, it is still persisting a little bit. So this is quite an interesting result. As for what we can do with it, we're still thinking about that. But nonetheless, we have found that the states with the most localized space-time trajectories are those which minimize position and velocity uncertainty. And they have an entanglement between their internal degrees of freedom and their center of mass degrees of freedom. But the key thing is that they are not our favorite Heisenberg uncertainty principle minimizing Gaussian states. And through especially the boost analysis, we can see that they are a correct description of idealized quantum clocks. So this result will be crucial for experiments which want to probe joint quantum and relativistic effects. And I analyzed with atom before, but in a molecular interference experiment, you can imagine that with even more internal degrees of freedom, this could get quite messy. So the delocalization effect there could grow beyond the size of even the molecule in a matter of minutes. And it's important to note that this localization is for all time. The mechanism behind why it stays together is not some sort of collapse and revival kind of effect. It is part of the way the state is set up. So once again, please check out our fresh off the press paper in PRR. And as for what I'm working on in this sense now, well, I'm looking next at angular momentum of these states, because these properties in the different momentum, the angular momentum regime, could be quite interesting. And of course, with all this talk of clocks on world lines, I can't resist looking into how we might apply this formalism to Unruh DeWitt detectors. So if you're interested in knowing more or have any ideas for future work, please get in contact with me. There's my email address there. And I think I've gone quite fast here. Thank you.
Yeah, that was quite fast. But,
I did not
thank
expect
you
to be
very
so
much.
fast.
No, that's all good. We're a bit early, so we've got plenty
Oh
of
gosh,
time.
I just looked at the time, very early.
It's all good. We've got plenty of time for some questions. So just raise your hand. You can use you just tap on the reactions icon and then raise hand to ask the question. Give people a bit of time.
Happy to go back to previous slides if I ripped through them a little too quickly.
Well, in the meantime, I can just ask, what are your thoughts on the what's next? Angular momentum and Unruh DeWitt detectors. What's that going to do?
Yeah, well, angular momentum, as we're finding, when you have a minimum uncertainty state between two angular quantities, let me think, say we're just using regular old orbital angular momentum, and you have the X state and the Y state in a commutator. On the other side of inequality between those is the third state. So for starters, a minimum uncertainty state in this regime is not as easily defined, because you do need this extra, you need to settle upon a value for the right-hand side of that inequality. And there's a whole regime, Stephen Bartlett's group about 10 years ago, we're looking at angular uncertainties between some angle and some, what's the other quantity? Between some angle and some, oh my gosh.
Oh,
sorry, words are escaping
radius? What, like total? What,
yep.
Total angular momentum?
Yes.
Is it? I'm not sure
it is.
Right.
Yeah, sorry. My brain is just on one track and in trouble moving to the other track.
Yeah, so you're talking about an angular coordinate versus a winding number? Is that the idea?
Oh, that is one, but
that's one, right.
But that's not the one that I was thinking of just then. Right. Yeah.
So there are minimum uncertainty quantum states for rotational objects.
Yeah.
So is that what you're talking about, or is this something different?
Yeah, it is.
Okay, right. So those are, they're spin coherent states and spin squeeze states.
Yeah, exactly. I would like to see if this can be translated to spin eventually, but I'm starting slow with general angular momentum.
Yep.
Yeah.
So with respect to the, and maybe I apologize if I missed it, but with the Unruh DeWitt detectors, so we had a group, myself and Valentina had a result with some Waterloo folks on delocalized detectors harvesting entanglement. Does this relate to that? And if you mentioned it, did I miss it?
Yeah, so you'll be familiar with Nadine Stritzelberger and Kim Kemp's work with the delocalized center of mass. So yes, there was I intended to work with them last year before COVID ruined my plans.
Yeah. I know.
I'm seeing if our two ideas there could somehow come together in some way. So I'm hoping to still have that work out someday, but yeah, that is the direction I'm looking at.
That's a good idea. We could have a look at it too, because Valentina and I were both involved with that.
Yeah,
work,
and
so.
you guys are
Same
local,
time zone,
relatively speaking.
Yeah.
Exactly.
Yeah. All right. Are there any other questions? Well, I think what we'll do then is thank Carolyn again. A little bit of clapping.
Thank you.
And yeah, and I think we'll just reconvene back on the schedule. So we'll have a 14-minute break, and we'll come back at 12:30 Melbourne time, 11:30 Brisbane time, and 8:30 p.m. Waterloo time. All right. I'll pause the recording for that period. Yep. Okay, so everyone, welcome back. So now we have two more talks for the session. Next is Koji Yamaguchi, who will be talking about building a block approach to asymptotic symmetries in general relativity. Take it away, Koji.
Okay, thank you for introduction, and hello everyone. I'm Koji Yamaguchi, a PhD student in Tokyo University. And in this talk, I will tell you about recent work on asymptotic symmetries in general relativity. And in this paper, we propose a new way to construct a building block of asymptotic symmetry in a spacetime. And by applying it to linear spacetime, we found a new class of symmetries on linear horizon, which we term superdilatation. So let's get started. As you may know, thermodynamic-like laws hold in black hole spacetime. And the entropy of black hole is given by this Bekenstein-Hawking formula. And from the viewpoint of statistical mechanics, it implies that it suggests that the black hole have microstates that can be physically discriminated from each other. And the microstate is will be labeled by the charges, that is a value of the generator of infinitesimal transformation. For example, in classical systems, the energy or momentum and angular momentum, etc., plays a role of the label or the charges. So in order to understand the origin of Bekenstein-Hawking entropy, we need to know what are physically non-trivial transformation or what are physically non-trivial charges in general relativity. So in order to explain it, let's start with the Einstein equations. Since the Einstein equations are invariant under diffeomorphism, it is sometimes misunderstood that all diffeomorphisms are gauge freedom, but this is not the case. And in order to explain or understand it, let us consider Lorentz transformation in Lorentz covariant theory. So as an example, let us consider a point particle in special relativity. And the action is given by this equation, which is invariant under the Lorentz transformation. And however, this does not, of course, this does not necessarily mean that the Lorentz transformation is a gauge freedom. And as an example, consider particles staying at a fixed point of the spacetime. Then the trajectory is described by this black line, or the trajectory is characterized by this x mu here. And the Lorentz, which is of course a solution of the equation of motion. And the Lorentz invariance implies that there is several solutions which is related through the Lorentz transformation. As an example, let us consider Lorentz boost. And after transformation, we have another solution described by this red line. So these two trajectory or solutions can be physically discriminated by the charges. In this case, the form momentum of the particle. And a similar argument holds for general relativity. The diffeomorphism invariance of the Einstein equation ensures the existence of solutions connected through diffeomorphism. And sometimes the charges can be used to discriminate them, and implying that the corresponding diffeomorphism is not a gauge freedom. So in order to investigate the phase space structure of the general relativity, we need to classify the charges. So that's why we will analyze the symmetry or asymptotic symmetry in general relativity. As a generator of an infinitesimal diffeomorphism along a vector field xi is known to be obtained in this formula. And the detailed definition of the integrants such as omega and S mu nu will be explained later. Here, what is important is that the bulk part of the charges vanishes by using the Einstein equation. So this symbol denotes the weak equality that holds, that is equality holds for holding for solution of Einstein equations. So as a consequence, the charges are calculated as an integral over the boundary of the Cauchy surface which we are considering. So it implies that the charge becomes non-trivial only when we consider diffeomorphism along a vector field that does not vanish near the boundary. So therefore, the research in research of symmetry or the charges in general relativity is called the asymptotic symmetries. And the asymptotic behavior of the metrics near the boundary play a crucial role to find any non-trivial charges. And there are various researches on asymptotic symmetries in general relativity. And for asymptotic symmetry on black hole horizon, there are well-known classes of asymptotic symmetry, which are the supertranslation and superrotation. And supertranslation is an angular-dependent time translation. So t is the label for time, and theta and phi is a coordinate system on the horizon. If f is a constant function, then this is usual time translation. But in general, we have angular dependence. And the superrotation is a diffeomorphism on the horizon. And in this early work by Masahiro Hotta and his collaborators, it is shown that the charges for supertranslation and superrotation on a Schwarzschild metric or Schwarzschild black hole can be integrable and has non-trivial charge algebra. And in 2016, Hawking, Perry, and Strominger wrote a paper on asymptotic symmetries as a possible origin of the Bekenstein-Hawking entropy, and they propose a resolution scenario black hole information loss problem by using the asymptotic symmetries. And their work stimulated other researchers, and hundreds of works have been done after them. But I do not go in detail about them. However, what is important here is that fact that the classification of asymptotic symmetry has not been completed so far. So in order to why this is the case, let me explain the conventional approach to find asymptotic symmetries. So the conventional approach is summarized in these 4 steps. First, we fix an asymptotic condition on metrics, and typically it is given by a sum of 2 contributions. The first one is the background metric, which we want to analyze, for example, the Schwarzschild metrics. And the second one is an additional contribution with a fall-off condition near the boundary. Then as a second step, we solve the asymptotic Killing equation to obtain the algebra of asymptotic Killing vector fields. And after identifying the metrics and the algebra, we can check whether the so-called integrability condition is satisfied to get well-defined charges. And if the charges are integrable, then we can finally check whether the charges take non-vanishing values. If the charge vanishes for all elements of the algebra, then it implies that the metrics cannot be discriminated by the value of the charges. So in this case, the diffeomorphism can be called a gauge freedom. So this is a conventional approach. Key point here is the fact that step 1 is quite important but difficult. We have to choose an appropriate asymptotic conditions on metrics carefully so that the charges are integrable. But even when the charges are integrable, if you are unlucky, the charge may turn out to vanish in the last step. And this is quite stressful since we may fail to find non-trivial diffeomorphisms after troublesome calculation on asymptotic Killing equation or the integrability. And our effort sometimes has spoiled. So we want to reduce such effort in trial and errors in this approach. And based on this observation, in this paper, we propose a new approach to investigate asymptotic symmetry. And the idea is simple but powerful. And as I have explained, in conventional approach, we start by fixing asymptotic conditional metrics. Instead, in our approach, we first calculate this quantity, that is the variation of the charges. And we fix vector field xi and eta so that this variation does not vanish at the background metric, which we want to investigate. And after fixing a set of two vector fields, we construct algebra A as the minimal algebra generated by these two vectors and their commutators. And by using them, we define the set of metrics so that the metrics are connected to the background metric by diffeomorphism generated by that algebra. So this condition provides a promising candidate for vector fields that is non-trivial charges. And in our approach, by construction, the diffeomorphism generated by this algebra is not a gauge freedom, since the metrics, these two metrics, G bar and G bar plus the derivative of G bar, can be discriminated by the charges. This is because that this quantity, that is the variation of the charge, is the difference between the charges that generalize the diffeomorphism along a vector field xi of the different two metrics. So this condition, we call this condition non-triviality condition. And I will explain the detailed flowchart of our approach, but putting this to be the first step to construct the asymptotic symmetry, we can analyze asymptotic symmetries in arbitrary spacetime. But as a demonstration, we analyze the linear spacetime. So linear coordinate tau yz is related to the usual Minkowski coordinate system Tx, yz through this equation. And the line element for the linear spacetime is given by this equation. And this coordinate system covers a light linear region, and the regional horizon is located at rho equals 0. And by using our method, we found a new asymptotic symmetry, which we call superdilatation. Superdilatation is composed by two parts, composed of two parts. The first one is a position-dependent dilatation in time, and the second one is a position dilatation in rho direction, that is the direction perpendicular to the horizon. So this is the one of our results. So far I have finished the introduction and the short summary of our result. And I will now move on to more. I move on to more detailed explanation. And I will first review the so-called covariant phase space method to find generator of infinitesimal transformation. And I will then explain our approach with which we can construct the building blocks of the asymptotic symmetries in arbitrary spacetime. And although our approach is applicable to any spacetime, we will finally analyze the asymptotic symmetry on linear horizon. And we will find a new symmetry, superdilatation, on the linear horizon. So the covariant phase space method provides a way to construct a generator of infinitesimal transformation in general relativity. And this method itself is applicable to general classical system, but I here focus on the gravitational system, a purely gravitational system, and start with the Einstein Hilbert action. And the variation of the Lagrangian is decomposed into two parts. The first one is the bulk contribution proportional to the Einstein tensor, and the second one is the derivative of so-called the presymplectic potential given by this equation. And by taking an anti-symmetric variation of this quantity, we can define the presymplectic current. And the variation of the generator is given by an integral over the Cauchy surface of the presymplectic current. And for solution of the Einstein equation, the presymplectic current is recast into this form. That is the variation, derivative of the antisymmetric tensor S mu nu, which is defined in this equation. And therefore, the variation of the charge is given by a surface integral of the boundary of the Cauchy surface in question. So this is why the asymptotic behavior of the metric becomes important. And since the variation of the charge is given by this formula, the charge are integrable if and only if the variation commute with each other in configuration spacetime. That is, this condition must be held to obtain a well-defined charges. And the left-hand side can be recast into this form, which is also calculated by using the tensor S mu nu. If the integrability condition is satisfied, then the charge is obtained by integrating along a path in the configuration space. So here is a flowchart of the conventional approach. In the first step, we fix an asymptotic condition on metrics, and then we solve the asymptotic killing equation to define the algebra of the vector fields. And after identifying algebra and the set of metrics, we can check whether the integrability condition is satisfied. If not, we go back to the first step and start with another asymptotic condition. And if the integrability condition is satisfied, we go to the next step and check whether there is any non-vanishing charge. And if all the charge vanishes, then it implies that the set of metrics cannot be discriminated by the charges. So we go back to the first step and start with another asymptotic condition. And if we could successfully find non-vanishing charges, then we get non-trivial charge algebra. As one can see from this flowchart, the success in this approach is highly depends on the choice of the asymptotic condition in the first step. And nevertheless, there is no guiding principle in this approach, so we have to make some effort in trial and errors. And in contrast, we have a definite guiding principle to find non-trivial charges in our method. We first calculate the variation of the charge as the background matrix for an arbitrary vector field xi and eta, which can be calculated by using the background matrix and the Lie derivative of it. And then we fix two vector fields xi and eta, so that the variation does not vanish as the background matrix. So this provides promising candidate to construct non-trivial charge algebra. And we then fix the algebra to be the minimal algebra generated by the vector field xi and eta, and we define metrics connected to the background matrix by diffeomorphism generated by the algebra. And again, in our approach, by construction, as a charge takes non-vanishing values since the variation does not vanish. But we have to independently check the integrability for the charges. Before going to the integrability condition for metrics, we will first check its necessary condition. That is the variation of the charge that does commute or not at the background matrix. Again, this quantity is calculated by using the background matrix and its Lie derivatives. So this is relatively easy. This can be calculated or checked relatively easy. And if this quantity does not vanish, then it implies that the charges are not integrable. So we go back to the first step and start with another vector field. So here is a complete flowchart of our approach. So we first fix two vector fields xi and eta so that the variation does not vanish as the background metric. And we then construct a minimal algebra spanned by these vector field and their commutators. And we then check the integrability condition as the background matrix. If it is not satisfied, we go back to the first step and start with another set of vector fields. And if the integrability condition is satisfied as the background matrix, we then construct a diffeomorphism generated by that algebra. And we finally check whether the integrability condition is satisfied for all metrics. And if not, we have to go back to the first step and try another set of the vector field. And what is important here is that this first trial and error step, in this step, we do not, the calculation can be done only by using the information of the background matrix, so which is somewhat easier than the conventional approach. And also, it is important that in our method by construction, as long as the charges are integrable, we automatically get non-vanishing charges. So as an application, we have analyzed the asymptotic symmetry on linear horizon. The line element of linear spacetime is given by this equation, and the linear horizon is located at rho equals 0. And we only consider a map, the diffeomorphism that maps a point in linear spacetime into itself. And then the asymptotic behavior of the generator of such a diffeomorphism takes this form, via A runs over Y and Z. And the first step of our approach is calculating this variation of the charge. And we have obtained this formula for linear spacetime, linear horizon. And from this formula, we can read out the vector field xi and eta so that such that this variation does not vanish. And of course, if we start with a different set of vector field, then we will finally obtain a different building block of asymptotic symmetry. So in this paper, we have analyzed two cases, this one and this one. So in the first case, we focus on this term. So if we take the vector field xi and eta to be this condition, then this term does not vanish, implying that the variation of the charge does not vanish. And in this case, xi corresponds to a super rotation, and eta corresponds to the super translation. And it should be noted that this is a class of diffeomorphism whose charge is shown to be integral in our previous research in 2016. But in this research, we followed a conventional approach to obtain this asymptotic behavior through trial and errors. But if we adapt our approach, however, this class of symmetry is naturally suggested by this guiding principle. So it reduces an effort in trial. It significantly reduces the effort in trial and errors. So this calculation shows that our formulation can be used to reproduce the result in our in previous researches. And here is a new one. In the second case, we focus on this term. If we take xi and eta to be this form, it can be shown that this variation does not vanish. The first one generates the position-dependent dilatation in time, and the second one generates the position-dependent dilatation in low direction. We term these transformations superdilatation. And we can check, in fact, we can check the integrity condition is satisfied for this class of superdilatation. And this is a new class of asymptotic symmetry on linear horizon, which we found by using our method. Okay, so here is a summary of my talk. Asymptotic symmetry are important as a possible origin of the Bekenstein-Hawking entropy, and the existence of black hole entropy suggests that there exists some microstate of spacetime which can be discriminated by the charges. And we propose a new approach to construct asymptotic symmetry, and it provides a guiding principle to find the building block of asymptotic symmetries. And although our approach is applicable to any spacetime, as a demonstration, we analyze the asymptotic symmetry on linear horizon, and we successfully found a new symmetry term, which we term superdilatation on linear horizon. Okay, that's all. Thank you very much.
Okay. Very nice. All right, are there any questions? Give people a chance to think if they would like. So I have a rather naive, just basic, super basic question. What exactly is a super rotation?
So what exactly is the super rotation? So, it's what exactly is this? So it's quite similar to the usual rotation, but it can be more generalized one since the generator can have a position dependence.
Okay.
So, I mean, just go back to see. Just a second, like this. So, this one should be better. So, in the case of usual or typical rotation, the generator does not have any position dependence, right? But we can. So this is a generalized rotation. Okay. And in the case of, for example, Schwarzschild, the horizon, event horizon or Schwarzschild metric, or the linear horizon, we can show that the charges, there exist charges corresponding to this rotation.
Okay, all right.
So it's a kind of general diffeomorphism on the horizon.
Yeah. Right. So this super, that doesn't have anything to do with supersymmetry then?
No.
Okay.
It's just an extension of rotation.
Yeah. Yeah. Okay. Are there any other questions? We're a bit early once again. Well, if not, we can thank Koji once again.
Thank you.
All right, so the next talk starts in 10 minutes. I'll hit pause this time rather than stop. All right, well, it looks like due to a last minute change, that's going to be the last talk of the session. So I think we're going to end this one there. We have another session next week at the same time, another Aussie session, and then the Waterloo ones will continue after that. But thank you all for coming.
Thank you, Nick.